We're going to go ahead and change gears now a little bit. You'll notice that the current reading on capacitors was actually in the same chapter as the field on potentials and things. But I'm going to argue, and I hope you're going to agree by the end of this next week or so, that we've actually started a whole new unit. And the unit we've started is about actual direct current circuits. Next week, we're going to actually start meeting currents and voltage in the context of a circuit and things like that. But today, we're starting off with capacitors. Capacitors are really fairly important parts of most circuits. They are, I think, perhaps given a little more attention in a lot of physics courses than they deserve. Not because they're not important, because just they're not as relatively important as they're often made out to be, but they are fairly important. So let me explain what a capacitor is and what it does. I'm going to take a battery. This is the symbol for a battery within circuit diagrams. And I'm going to hook it up with some wires to two parallel metal plates. Okay? The battery has voltage V. That means the positive charges want to go this way, and they build up on this plate here. The negative charges go that way and build up on this plate. So we could actually disconnect the battery at some point if we wanted to. And what we would find if we did that, go ahead and open the circuit up. So now there's no more battery enforcing voltage, but when we did that, the positive circuits are trapped on the top plate here. Oops. The top plate, and the negative charges are trapped on the bottom plate. So the result of that is that we have this charge separation across the plates. Well, I'm going to zoom in a little bit on this. Take a look at the plates. We've got positive charges up here and negative charges down here. Notice we're going to have the same number of positive and negative charges on the two plates. So if I've got a million positive charges on top, I have a million negative charges on the bottom. Okay, that's really important. Well, what's the field in here look like? Well, near the middle anyway, it's going to look kind of like this. Now, near the outside edges, things get a little wacky. The thing starts to actually bow out a little bit. I'm just telling you that. You don't need to know this, but it is. You might find yourself asking about that. But in the middle, it's pretty much uniform. Electric field E. Now, we've talked about how much charge would be here for so much voltage, in the sense that we know of a relationship between voltage, V, and electric field, E. If we know the distance between the two plates is D, the voltage is ED. We did this in class last week. But I can also tell you something about E. On a problem in class, I asserted, and you don't have to know this, but though it is on your equation sheet, that the electric field goes like sigma, the charge density on here, over epsilon naught times D. Well, that's pretty cool, but you know, what's epsilon naught? Epsilon naught is the charge per area, so the charge Q we've put up here, and minus Q down here, over area, epsilon naught times D. This is the capacitance equation. I'm going to rewrite it up here. This basically governs the voltage I apply and how much charge I get on the other plate. We can rearrange this if we want to and say that A epsilon naught over D times the voltage I apply is how much charge I get, okay? That's pretty cool, but we can actually, for a given arrangement of plates, distance between them, size of the plates, etc., we could actually just make this a different variable. We'll call it C for capacitance, V equals Q. This is the capacitance equation. C is given. It's in units of farads. A farad is a coulomb per volt. Okay. And it tells you how much charge is on the capacitor for a given voltage you apply. Or if you want to rearrange it, you say, tell me how much charge you've put on it, I'll tell you how much voltage it's holding. Now, I can change the capacitance of my capacitor three different ways. The first way, I can make the plates bigger. Okay? That's a good approach. I mean, one way you can make plates bigger without getting crazy about it, by the way, is to roll the plates up into kind of a jelly roll, spiral from the side. So they're a long cylinder from the outside, but inside you've got these plates wrapped up around each other. Okay? If I make D smaller, if I get the plates closer and closer together, the overall capacitance goes up as well. Finally, this epsilon naught. Now, I can't change epsilon naught. That's a constant of the universe. However, if I stick a different material, not a vacuum, between the plates, it effectively changes this constant. The reason it's epsilon naught, not just epsilon, in fact, is there's a whole range of epsilons. Different materials have different epsilon values. So if I put something with a higher epsilon in there than a vacuum, I can actually get a bigger capacitance. Okay? And that's actually really quite cool and quite helpful, okay, for building capacitors. Next, in the next video, I'm going to show you how you calculate capacitance for having multiple capacitors together. And then in the third video, I'm going to tell you about what capacitors are really, really useful for. Okay?